Well, I'm still wondering where some people are, but tired of waiting for them. Since we have several of you who ever do teach or will teach, maybe for a career or as a graduate student, what they don't teach you about classroom management, if you will, is that when you are saddled with a lack of proper classroom resources like chalk or erasers or markers, yeah, that sort of thing, that if you complain enough about that, it's certainly true of USM, it's always the case. If you complain enough about that in front of your students,
somebody's going to buy you one.
Yes.
That's true.
And that's how this eraser got here. And
another thing, don't leave it in your classroom because other teachers will steal your stuff.
Oh, gee.
Yeah.
Can't imagine that anyone would ever do that.
I teach at a private Christian university, and they jack my stuff all the time.
Well, yeah, and then no classroom is safe.
Well, it's a private Christian, high school, university, whatever.
Okay.
The point is, Christian school, and they still steal your expo markers. That's why I carry a bag around with me.
Yeah.
They're mine.
Thanks, Trey.
Yeah, and if you don't put the lid back on her marker, she gets very angry.
And she's like, "These are drying out," and she walks around with it open for 5 minutes. I'm like, "Yeah, that's why."
Thank you.
Yeah. Well, yeah. No, like Candace has a whole tub full of markers. And,
Yeah.
Yeah. So apparently, it's required things that teachers are required to pack. Okay. Now, feels like forever since I've been in this class. So it's taken some time, effort to get back into the swing of things. Well, yeah, it has been almost 2 weeks. So now, for the schedule, I had put the upcoming, well, definitely no longer a midterm because it'll be well past this halfway mark of a semester. But test, the one and only test we'll have besides the final. For Tuesday, April 3rd. But then that would mean that I'd set aside the previous class, so not this Thursday, but next Thursday, March 29th, for a review. And the problem is I'm away on that day. And I thought, well, okay, I'll get a sub, not for a review. And if I was missing a class where they'd be like covering a topic,
Amber would teach.
What?
Said Amber would teach.
She would be the best choice, but
She got her own job.
yeah. So we're just not. So we will not have class on the 29th, and then what that means though is that the 3rd will be the review, and then Thursday, April 5th, will be the day of the test. I haven't updated the site with that modification, but I will soon.
That's the 29th, right?
So Thursday the 29th is when there won't be class.
4, 3.
Okay.
Test 4, 5. There you go.
Yeah, because
I gotta go home early.
that's right, you do.
Oh, yay.
Yeah.
I might be able to see my husband.
Okay. Oh, there's a perk. Okay.
I might. He might be at work until 10.
Okay.
Obviously.
So then, the other thing is, while on the subject of the test, okay, actually I'll put this on the board for people watching. So.
This is 461, right? Mike, 461?
Yes.
Okay, thank you. No, because I have it here that we have a midterm, that 27th on, like.
That's a modern algebra midterm that I was trying to avoid a conflict with.
Yeah.
We had it originally on the 27th.
Yeah, that's how I was about to
Oh.
say.
That's why she was erasing it because she had
Oh,
both
I
of them
see.
on there.
Okay.
She's making sure her code was right.
I was like, how do you know what number of class you're sitting in? Okay.
I never know the numbers. Yeah, the new test day. The new test day. Are you sure we're gonna take this test?
I don't think we should.
I agree.
I'm serious.
You just want a final exam?
Well, that's the same day as our problem sets two test.
Oh, problem
Which is a lot
stats
better
too.
than mine.
Yeah, it's a lot better. It's a
It's
lot
a lot better
easier.
than
than
mine.
mine,
I'll
I
take it,
promise.
yeah.
I'd rather put those two together.
Me too.
Okay.
Me too.
All right. Okay, because I can't jerk us around
We'll
anymore.
get Paris to move it.
Oh, okay.
That's Paris.
He really
He
might.
would.
Well,
Yeah.
the thing is,
I've
there's a
asked
good
him.
chance he'll ask me to proctor that one. So,
Well,
yeah. So,
All of a sudden, it's open book.
yeah, because a lot of times he asks me to proctor, and I can't for whatever reason. But yeah. So, yeah.
He did that once for us. He
Yeah.
came up for us, but that's because he didn't have anybody on the coast.
Oh.
So he literally just sat in an empty classroom on the coast and taught us all up here.
Oh,
It's
okay.
very awkward.
So I do have a practice test for you.
Yes,
Oh,
it's
that sounds
online.
awesome.
It's already posted.
So hopefully that would make
Already
you
posted.
more amenable to actually taking it.
Don't memorize it.
Yeah, I'll talk about that in a moment.
Okay.
So this is on the lectures page. And actually, I'm going to pull that up here so I can remember what I put.
I'd look it up.
But yeah, I'm not changing it. I basically put together what was most convenient for me, because making up test problems is a huge pain. So there are now, what you'll see in the practice test, there's a total of 6 problems. Now there's okay. So what you'll see in the real test are 6 problems of the same type, and then there's also, I'll talk about concept questions after that. So so what you see there is like applying a bisection method to make progress towards finding a root of a function.
On the practice test?
Yeah, and therefore would be in a real test. Fixed points, iteration. Now it's not just apply the method, but questions about convergence or existence or uniqueness of a solution. So that theory behind fixed point is on the test. But you'll see the kind of questions, things that you would need to know. Okay. And then Newton's method. And I actually have 2 questions about fixed point iteration. The method I'm going to cover today is a secant method that's closely related to Newton. So I'm opening that door. That could be on there, like might be secant instead of Newton's method. So basically, there's 4 problems that are on root finding methods. Okay. And then, okay, so the other 2 problems are on Gaussian, I'll put it under the umbrella of direct methods. For AX equals B. And by direct methods, I mean Gaussian elimination with pivoting, like partial pivoting, like you did on one of the homeworks, or if a matrix calls for it, like a Cholesky decomposition. So it'll be one problem from that chapter. This is chapter 3.
All 12 steps.
What?
Nothing.
Okay. And then one problem on iterative methods. For AX equals B. That's from section 5.1. So the problem on the practice test features Gauss-Seidel. So we were looking at Jacobi, Gauss-Seidel, SOR. Can you carry out these methods? And so I'm giving myself a little bit of wiggle room here. Like for instance, if a problem practice test is Gaussian elimination or partial pivoting, that might be a problem in a real test, but you can't hold me to that. It's one of these direct methods, though. I will promise you that. If a problem in practice test features Gauss-Seidel, I might switch it up and say Jacobi. So that's what you have to be prepared for. Now, some of you have a question?
We could do the test like you did in DE, like we'll take it one day and then we'll
Oh, right, forgot about that.
look at it and not correct it.
Okay.
Is that the one I proctored?
Yes, it is. Okay. Yes, I suppose that is, if you're now on the other side of that. Okay. That means eating up part of an additional class period.
Don't you only give us like part of the time?
I do. Well, okay, so here's what I'm going to do. Okay. So the first part of class on April 3rd, much of it will be review. Then you can start it on the 3rd. And then you'll have the entire class period on the 5th. So basically, think of it this way. The exposure you get on the 3rd is a chance to get over whatever freak out you're going to have when you get a test. Because then when you come back on Thursday, you'll see, okay, this is what you were in for, and you can calm down and finish it. All right. Now, this is what you see on the practice test. Also, I have there is a page of formulas. It gives formulas, for instance, for fixed point iteration, Newton, secant. Some results, theoretical results of a fixed point. I put Taylor's theorem on there. I'm not sure if it'll be necessary, but why not? So you'll have that for your reference. So what you see in a practice test is what you'll have available during the real test. Now, the other thing that will be on the test, this is not included in the practice test, is lightning round. Basically, the kind of questions that you see in the quizzes. So I'll put a bunch of those on there. So your best bet studying is study the quizzes. Don't memorize the quizzes. Okay. Do not memorize a practice test.
You know how many questions you'll do?
I have not decided that yet, but I will tell you beforehand, like on
4.
Thursday or something.
Okay,
What?
then 10 questions.
What?
I said 4.
Oh.
So we have 10 questions total.
Oh,
That could be 4. That's just way too few.
Okay, then 14. We have 20 questions total.
That's closer to That's
Okay.
okay. I'm not deciding anything yet.
Mhm.
Okay. All right. 'Cause I need to think about how much time you have and all that. Okay. So one thing, on the one hand, I feel like it's a good idea to give practice tests because I don't want a situation. For one complaint I hate getting, and I realize in other classes, many classes, it probably is a valid complaint. This test was nothing like what I expected. Well, you're seeing exactly what to expect. And several years ago, some idiot still made that remark even getting a practice test. It's like,
Oh, that's awesome.
yeah, I let him have it. There's just no excuse for that. It just means you weren't paying attention. But sometimes it has been. I normally do this in lower level classes because in higher level classes I don't always give in-class tests. But I've been prodded to do that by powers that be. So that's the unfortunate thing for you. Um, so, one of the downsides of giving practice tests is that students will simply memorize this on the practice test and give that answer, or treat it exactly like it's exactly the same problem, not realizing that there are differences. The practice test is not meant to tell you what's on the real test. It's meant to tell you what types of problems will be on the real tests, and also how the problems tend to be worded, things like that. So you're not thrown by that either. It's not meant to give something away. So if you, so for instance, if I ask a question like in a lightning round section that's related to something you've seen on a quiz, but it's not exactly the same question, don't write down something that you memorized from a quiz, because that's going to be flat out wrong. And not only that, but I'll know that that's what you did because I've seen that before. Oh, right.
My apple stopped being lit. I was like, I fell asleep.
Okay. So if you do that, I'll know it because I know I've seen this done before. I recognize what kind of answer that would be. And that's just going to piss me off and make me take off more points than I might otherwise from intent to honestly trying to answer the question and happening to get it wrong. Because I will give partial credit. So don't be lazy about it, because it will go badly for you, I promise. So please keep that in mind. But if you look back at the quizzes and understand what you put on the quizzes, as opposed to copying and pasting what seemed to be the right portion of a book, hint, hint, then the section will go well for you. So that's why I'm putting it on there. I want to see how much of that, if anything, sank in. Okay, and this counts for 30% of a grade. And then, then when it comes time for the final, similar format, there'll be more time, of course, but it'll be, and the final will be comprehensive, but it will focus on material that comes after this, like from upcoming chapters, like on differential equations and so forth. Same thing for lightning round. There will be those kind of questions, again, mostly focused towards the end. I'm weighing whether I want to do the oral final thing, like I have in the past. Some of you did that last time. I'm open to that. So, are any questions about the test, the midterm?
3/4 of the way.
No? Okay. So go ahead and take a look at that practice test. And with a practice test, there is a solution. So what I would suggest is just look at the practice test first, try your hand at it, and then you can look at the solution later. Okay. As far as now, there is another homework. I need to post this. Actually, I'll go ahead and write it down on the board now, but then I'll put it on the site. So, homework 6, and this is in section 10.4, which is what I started covering the last class before break on Newton's method, and then I'm going to finish today on a secant method. Not quite as many problems, so it's section 10.4, explorations 3 through 8. And that will be, well, you know how I am about due dates. So that would be, the day of the review is when I recommend finishing that, because there will be, one of the regular problems will be on this section, at least one, possibly two, and certainly some of the lightning round questions will be on that section also. But I just want to put this out there right now, and then I'll update the site later with all of the schedule changes. So, okay. And then we have homework 5 that you guys are presumably working on now. Hopefully. Any questions about that? Because that will certainly feature prominently on the test as well. Okay. Have all of you at least started it?
I thought I had submitted it.
Well, basically, if I get an email that's a homework submission, I just like quickly file it
Okay,
in
sounds
in
good,
my
yeah.
to grade folder, and so I have it. Okay. All right. And by all means, feel free to ask me questions. I know this goes nowhere, but still, I have to try. Outside of class if you don't feel like asking in class. Okay, so, but no one has any questions now. It's just so easy. You shut up. Okay. All right. I know what the answer is to that question in your case. Okay, so, all right, so now that I've burned some minutes on that, we'll finish off this section, and then that'll be all the material for the test. First, a recap is in order.
It's the first day of school. It's cold.
Okay, now, so one of these methods has been covered already, Newton's method, and since it's been such a long time since we've been in this class, let's call it a problem we're solving f of x equals 0, so we're root finding, and Newton's method is you make an initial guess. I'll call x0, and then the actual iteration that you perform to get closer and closer to a root is xk plus 1 is equal to xk minus f of xk over f prime of xk. And we keep doing this until hopefully it converges. What we saw was one example last time where it failed miserably. Now, there are key properties that were learned. Is that the convergence is quadratic. But only if f prime at the root is non-zero. Now I did an example last time where the convergence turned out to be linear in a case where f prime is 0. And one of the homework problems that I assigned just now is to actually prove that, like I did a convergence analysis, so now you do a similar analysis that where you show that, so the asymptotic error constant, that I refer to as capital C, in the quadratic case it is f double prime at the root over 2f prime at the root. Whereas in the case where you have a double root, if f prime is equal to 0, the c is equal to 1/2. So I showed that in an example last time. So one of the homework problems is to show that this actually is true in general. I should say if it is a double root. if it is, so in other words, f double prime is still non-zero. So for a homework problem, you can make that assumption. If it is a root of higher multiplicity, so like a triple root or quadruple root, or so on, then the constant is different. So and we're not going to get into that. Okay, so this is the convergence behavior that we have, and so one other thing to know about Newton's method, very important property, is we saw this last time. One of the drawbacks of Newton's method is that in general you need, in some sense, a good initial guess. We saw an example of a case of computing a reciprocal without performing any division. That if I chose a poor initial guess, the iteration diverged wildly. So this is one unfortunate thing about Newton's method is that you'd like to have an initial guess that is reasonably close. It's not like bisection, where you can have a very large interval, but if it changes sign, then bisection is guaranteed to converge. So those kind of guarantees are generally not possible to have with Newton's method. But I just realized that this is something I forgot to cover last time, or I ran out of time. There are situations where you can get some assurance that Newton's method will converge. And I assigned one of these for homework, but I'm going to show you a similar one now. So then when you go to a homework problem, you can follow along with this. Okay. So here's an exception to this rule of thumb, where you don't necessarily need a good initial guess. Suppose that the function is so the first derivative and the second derivative are positive on some interval I that starts at the root and continues off to the right. Okay. Actually, I can make it a closed interval. Okay. And the idea here is delta here can be anything. It doesn't matter. It doesn't have to be small. It could be It could be extremely large. We don't care. Now, when a function has its first and second derivatives positive, what does the graph of that function look like? What can we say about it? Remember your calculus 1. I know it's a tall order for some. Yes, like that, as you described with your hand there. Yes. So it is increasing and concave up. So it behaves something like that. And let's suppose that the initial guess, or our latest iterate, so here's the root, x star. So let's suppose that our current iterate, xk, is over here. So in other words, it's in this interval. Okay. So in other words, in particular, I want to assume that xk is greater than x star. So, but the thing is, xk is allowed to be far away from it, very far. But now let's see what happens when we actually perform Newton's iteration, perform Newton's method in this situation. because now when you compute the new iterate using Newton's method, now, the thing is, this part right here is positive by our assumption that the function is increasing. Now, calling our graph, here's x star. Past this point, the function is increasing and concave up. So in other words, this function value here, which is f of xk, that has to be positive also. Okay. So we're taking xk, we're subtracting off a fraction from it that's going to be positive. So what this means is xk plus 1 is strictly less than xk. So in other words, the sequence of iterates is a decreasing sequence. Okay. Now, one other thing that we can say, you look at the error. Well, the error from, this is taken from the previous error analysis I did, so you would find this in your notes from last time. I'll just repeat the conclusion here. Is second derivative at some unknown point over 2 times the first derivative at xk times the previous error squared. Okay. Now, this unknown point has to be between x star and xk. So what that means is it's in our interval. So in other words, this is positive. First derivative, also positive. This squared part, positive. Everything is positive. So what we can conclude from that is xk plus 1 is greater than x star. So if we put the two together, we have our new iterate is between our exact root and our previous iterate. So we have a decreasing sequence of iterates, but it's not allowed to decrease arbitrarily. There's still a barrier here.
Is that just a squiggly line?
Here?
Yeah.
Yes.
Okay.
Well, the Greek letter xi, but yeah,
The Greek letter what?
xi. Yeah, like if I were to draw it properly, it'd be something like that.
Okay.
Yeah. Yeah, that's. I just go with squiggly. All right. So not only is this sequence decreasing, our sequence of iterates is bounded. It's bounded by our initial guess, whatever that is, and on the, above, and it's bounded below by the root. Does anyone know what we can say about a sequence that is bounded and decreasing? I remember teaching about this in Cal 3. It'll also come up in real analysis. Yes. So a bounded, decreasing, it's decreasing in this case, but any monotone sequence, increasing or decreasing, sequence converges. So these iterates that we're generating by Newton's method, they're going to converge to something. So now the thing is, we have to be absolutely sure that what it's actually converging to is the root. So what we can say is xk converges to, and watch carefully here, x sub star. Now, for root, I've identified as x superscript star. This is x sub star. So superscript, subscript. They're different, or they're allowed to be different. So this is a notation that's used in the book as well. But I need to show that they actually are the same. I haven't shown that yet. Okay. Now, if we look at our Newton's formula, xk plus 1 minus xk, if I just, those are not vectors, what am I doing? The difference between two iterates is equal to f at xk over f prime xk. Now, the difference between two iterates is going to 0 because, so this difference goes to 0. Therefore, this difference also has to go to 0. So that means that f at our limit is 0. That's the only possibility left. So x substar is a root. But we've already concluded that f is positive. For x greater than a root that are in this interval. Therefore, x superscript star has to equal f sub star. So xk converges to the actual root. Yes?
It's F prime on the top, I mean on the bottom of the.
On the bottom, yes, this is prime. Yep. Okay. So, in this situation where we have no assurance of the initial guess being anywhere near the root, it could be far away as you want, but because f has these properties of being increasing and concave up after the root, if you go ahead and perform Newton's method, it will converge. And convergence will also be quadratic. So one example that I did of this was using Newton's method to compute a square root. Now, I just chose an initial guess of 1 to compute the square root of 2, but I could have chosen any initial guess. I literally could have chosen an initial guess of like 1,000,000, and it still would have converged. It would have taken more iterations, but it still would have. So these kind of situations where f is nicely behaved in this way, you can still get convergence even if your initial guess is awful. Now, so one of the problems that I assigned, problem 6. So I'll just write it here. So for problem 10.4.6 gives a different situation where f is still increasing, it's concave down, and your initial guess is less than the root. So the general flow of your argument is going to be exactly the same. It's just that the particulars are going to be different, right? And you're still going to reach the same kind of conclusion. But then I also ask, what if the initial guess is greater than a root? How come it doesn't work in that case? And if you look at like how the graph of f behaves in that situation, you'll be able to figure it out. I'll post this in the hints. I haven't made up hints for this assignment yet. So, but I wanted to step through this argument here so you can basically mimic it for the problem I've assigned. Any questions about what happened here? And this is written up in the book also. Now, if we go back to Newton's method, as I've written it here. Okay, now, so one drawback is it can fail if you have a bad initial guess unless you have certain nice conditions like I've just shown you. But if you think about the other methods that we've seen, bisection, where you just plug some points into F and it'll converge it slowly. There's fixed point iteration, where you write the equation as x equals g of x, and you just keep plugging into g. And here we have Newton's method. What makes Newton's method less practical than the other methods that we've seen? So the other methods were just plugging in various points, carefully chosen points, into our function f or our function g. What makes this method more of a pain to use?
You have to have the derivative.
Yeah. So we have two functions to work with, f and its derivative. If f itself is a particularly complicated function, its derivative could be quite monstrous if you have to use like the product or quotient rule to, dang it. Okay. Yeah.
That's my call.
Well, I could bring it over. But, okay.
Oh, dang it, that's my time.
Yes, I guess it is.
Could be worse.
What?
What's ever convergence?
Oh, convergence? Oh, okay. Well, of a quadratic convergence. Yeah, Newton's method is quadratic, unless it's a multiple root. Yeah. Yeah. So in that sense, so this makes Newton's method really the best method we've seen so far because it could converge the most rapidly. Yes.
Is that the case for decreasing functions of?
Oh, well, okay. This situation right here.
Yeah, the exception for that.
Yeah, if it's concave up and increasing. Now, so in other words, there are other situations like this where you also get quadratic convergence and guaranteed convergence, even if you're far away from a root. So one of the homework problems describes one such situation. Okay, well, for example, here we have three conditions: increasing, concave up, and your iterates are greater than the root. But suppose I change the situation, so this will become important for the homework problem. Because if I'm over here and I draw my tangent line, and remember that's how Newton's method works. You do the tangent line approximation and you find its x-intercept, and you can see that Newton's method is working the way it's supposed to. That's getting closer and closer to the root. Now, I'm going to draw a different situation. Suppose I have f is still increasing and concave up. So f prime and f double prime are positive. But now, I've chosen the initial guess over here. So it's less than the root. So in this case, actually this might still work but then again, it depends on how well this function behaves, because now my tangent line is going to take me way over here. So in this case, we were counting on the iterates staying between these points, and they do. Here they don't. So my tangent line is going to take me past the root, and then who knows what happens. You would need assurance that it's still increasing concave up over here, and maybe then it'll converge. So some situations you can guarantee convergence, but Others you can't. So, and the thing is, if you don't know how f is behaving over here, Newton's method might fail. Okay. But yeah, in these situations like this one, where it works, the convergence is quadratic. So in other words, this situation applies. A good situation. Okay. Now, but now we have this hassle of having to compute a derivative. And when you have actual mathematical software where the user has to specify what function f you want the root of, if you're going to use Newton's method, then they have to compute the derivative. And so you're imposing an extra burden on the user. And what if that function is very complicated? And they're like, no, I don't want to use this method. That's a pain. I'll use something else. So now I'm going to show you a modification of Newton's method that gets around this requirement of computing a derivative. Actually, I'm going to leave that there. Okay, back over here we go. Okay. You guys wondering, like, how am I going to spend 75 minutes talking about the secant method? I don't really feel like doing that. But now I don't have to because there's only 25 minutes left. Okay. So even when you guys don't ask any questions, I can fill up time. All right. So the secant method. The easiest way I can describe it is Newton's method without derivatives. So the iteration xk plus 1 is a similar form. So it's equal to xk minus f of xk. So when I start writing it, it looks exactly like Newton's method. But now what I'm going to do is I'm going to replace the derivative by a difference quotient. So that would be f of xk minus f of xk minus 1 divided by, well, I'm replacing a derivative by that. But a derivative in Newton's method is in the denominator. So what I'm dividing by goes up top. So this right here, this difference quotient, is an approximation to f prime at xk. And in fact, as the iteration converges, if it's converging, this will converge to f prime at xk. So it will behave more and more like Newton's method as you get closer. So that's the method. So this is secant method iteration. But notice each new iterate depends on the previous two iterates. So Newton's method, xk plus 1, comes from xk only. Xk plus 1 requires xk and xk minus 1. So a consequence of that is it requires two initial guesses. Which I'll label as x0 and x1. So once you have x0 and x1, then you can use this formula to compute x2. Then you use x1 and x2 in this formula to compute x3, and so on. So this iteration is for k equals 1, 2, and so on until convergence. But at least now we don't have to computer derivative. So you're trading one piece of information for another. Like so, before you had to ask a user for f and f prime. Now you only have to ask a user for f and a second initial guess. And what they might do is they might say, well, just use the first initial guess, change a little bit, if they don't have any other good way to choose it. Now, so for a contrast between, or I guess compare and contrast between Newton's method and the secant method. In Newton's method, the meaning of xk plus 1 is the x-intercept of a tangent line of f at xk. So that's how the formula for Newton's method was derived. We just find out where that tangent line is equal to 0, and that's the new x. Whereas with the secant method, xk plus 1 is also an x-intercept of a secant line for these 2 points, xk minus 1 and xk. So to show you what that means graphically, so let's make up an example here. So let's suppose I have my first initial guess, x0, second initial guess, x1. So then I mark these 2 points in the graph. So now what I do is I draw the line that passes through those 2 points, which you can see kind of looks like a tangent line. And in fact, the closer those 2 points are, the more of a tangent line it'll be. And then I take its x-intercept, and that gives me x2. And now I'll use x1 and x2, draw the line between those 2 points, get its x-intercept, and that's x3. And then I take x2 and x3, draw a secant line, and now my graph's getting a little cluttered. But you can see we're getting closer to the root again. So, and also, as the points are getting closer together, if I have 2 points on the graph of a function that are very close to one another, and I draw the secant line that passes through these 2 points. That's very bad drawing. That's going to look more and more like a tangent line. That's still a bad drawing, to be honest. It really should look more tangent line-like. In fact, I'm kind of embarrassed by that. Let's try it again. So, don't put that in your notes. Okay. Yeah, better. Okay. Yeah, it's almost a tangent line. And that's just going to keep getting more and more like a tangent line. So in that sense, it's a good approximation to the secant method without having the burden of evaluating an extra function. Because each iteration of Newton's method requires 2 function evaluations, one for f, one for f prime. Secant method, you only have to evaluate f at your latest iterate. Like this is something you'll already have from the last iteration. So there's only one new function evaluation. So in other words, the secant method is about half the expense of Newton's method per iteration. But then what are we giving up? Because now we're using an approximate tangent line instead of the the true tangent line. So what can be said about the convergence? Yes, it is going to be slower. And so to try to get an idea of what the convergence behavior is like, is there a question?
We can tell if it was a -1 or a +1 at the bottom, but I think it's a minus, right?
This is a minus.
Okay, that's what we thought.
Okay. Yes, I know my writing is awful, so feel free to clear it up at any time. Okay. All right. So to try to see what's going on convergence-wise, it's a little more difficult to analyze because of using values up at 2 points rather than 1. All right, see if I can do this in about 10 minutes or so. All right, so what I'm going to do is I'm going to assume that it's a simple root, so f prime at the root, which I'll call m star, is positive. Because it's when it's equal to 0, that's when we have problems with convergence. That's true for Newton's method, and it would be true for secant method also. Now, I'm going to let alpha be a constant between 0 and 1/3. Now, I'm also going to assume that f prime is continuous. So what that means is, by continuity, since f prime is positive at a certain point, the root, it's going to be positive near that point also. So a consequence of a continuity of f prime, there exists some value delta so as long as I choose delta small enough, this works. Small and positive. Such that f prime is bounded by 1 plus alpha times m star, and then bounded below by 1 minus alpha m star. On the interval x star minus delta, x star plus delta. Now, this seems kind of strange, I admit, but the point is, if I require that x not wander too far away from x star, then f prime cannot wander too far away from m star. I'm just imposing limits on f prime using this constant alpha here. Okay. Now what I'm going to do is perform a convergence analysis of secant method, like I did last time for Newton's method, using Taylor expansion, and see what we get. Okay, so what I do is so the way proper convergence analysis goes is you look at xk plus 1 minus the exact root, and then you, on the right side, you put the formula for xk plus 1 minus the root. So I'll fill in the formula for secant method. Okay. And then I have minus x star. So subtracting it from both sides. And then what I'll do is, okay. What did I do here? That's weird. Okay. Yeah, it's like, all right. Now I remember. Yeah, so the things in the book I kind of skipped some steps. Now, this expression right here, I replace by f prime at some unknown point, which in the book I call phi k. And this is by the mean value theorem. And I can say that the unknown point phi k is between xk minus 1 and xk. Because mean value theorem says f of b minus f of a over b minus a is equal to f prime at some point between a and b. So that means I would put this f prime down in the denominator. Okay. Now, so that's one replacement I can make. But now I can use the mean value theorem again. Mean value theorem also says that f of xk minus f of x star over xk minus x star is equal to f prime at some point which I'll call theta k. And theta k is between x star and xk. So I want to use that in my expression down below. But I can simplify this. What is f of x star? 0. X star is the root. So that's gone. So in other words, I can say that f of xk, which is in my expression down there, is equal to f prime theta k xk minus x star. So now I can substitute, whoops. Sorry to those watching at home. Okay. All right, so now I can make this replacement in what I have down here if I'm boxing. So I make that substitution, and what I get is xk plus 1 minus x star is equal to xk minus, and I'll have f prime of theta k xk minus x star over f prime of phi k, and then I still have a minus x star, which actually I'm going to move over here just to put things together. Okay, minus all that. Okay. Now, here I have xk minus x star. Here I also have xk minus x star. Factor it out. So then I have 1 minus f prime of theta k over f prime of phi k, all times xk minus x star. So in other words, the new error is equal to the previous error times this large expression in the large parentheses. So now I want to know what happens to that. Does it approach a constant, in which case it's linear convergence? does it go to 0, which would mean better than linear convergence? We need to find that out. Okay. Now, the thing is, f prime is like, because of the limits on theta k and phi k, like theta k is between x star and xk. Phi k is an unknown point that's between two iterates. So if my iterates are inside this interval that I've laid out, where f prime satisfies these conditions, then I can take advantage of that. Because I want to try to get a handle on how large that fraction can be. So since f prime is greater or equal to this, less than or equal to that, but the problem is, okay, so I repeat this. I don't know if this fraction here is greater than or less than 1. It's positive, but that would affect the sign of this. So if I take the absolute value of both sides, then I can say this is less than or equal to the maximum of 1 minus 1 minus alpha over 1 plus alpha, or 1 minus 1 plus alpha over 1 minus alpha times xk minus x star. And it's because I don't know if this fraction is less than or greater than 1. So because that would affect whether this is positive or negative. So that's why I have to cover my bases by having either the lower bound up top and the upper bound down below, or vice versa. So that way I know that this, whatever's multiplying the previous error, cannot possibly be bigger than either of those two things. Okay. So I'm going to try to simplify this. Use a common denominator. In both cases. Okay. So here, if I combine these fractions, here the ones will cancel, and I'll get 2 alpha over 1 plus alpha. And over here, the ones will again cancel, and I'll get minus 2 alpha over 1 minus alpha. Now, I'm taking the absolute value. This denominator is the smaller one, because alpha is less than 1/3. So this is less than or equal to 2 alpha over 1 minus alpha xk minus x star. Now, this fraction here is guaranteed to be less than 1 because alpha is less than 1/3. And if I plug in alpha equal to 1/3, I would get 1. As alpha gets smaller and smaller, this fraction is going to 0. But the thing is, alpha can be any number between 0 and 1/3. That's the only assumption that I've made here. So now what I can do is, because this right here, this fraction, that's C. That converges to C. That's the asymptotic error constant. So what we have is, I've established linear convergence. And C is, actually it's less than or equal to 2 alpha over 1 minus alpha. For whatever alpha I've chosen between 0 and 1/3. But I can choose alpha to be any number between 0 and 1/3. So what this means is I can let C go to 0 by letting alpha go to 0. So I can make the asymptotic error constant 0. So what happens when you have linear convergence, but the asymptotic error constant is 0? Superlinear convergence. Okay. So, not quite as good as Newton's. Newton's method converges quadratically, but still quite good, better than the other methods we've seen that converge linearly with a positive asymptotic error constant. Now, what I haven't taken the time to show here, oh God, I'm late. Dang it, so sorry. Okay, very quick. So the actual order of convergence, which I labeled as R, it's actually, and this is shown in the book and a combination of homework problems I did not assign, it's actually 1 plus the square root of 5 over 2, which is approximately 1.618. So between 1 and 2, closer to 2. And that number is known as the golden ratio. I don't recall the formula for C off the top of my head. It involves, it's actually a power of a constant for Newton's method, which involves f prime and f double prime at the root. So the thing is, here's a trade-off. You don't need a derivative, so your iterations are faster. It converges a little slower than Newton's method, so it takes more iterations. Which factor wins? A lot of people actually prefer the secant method, that having the less expense per iteration is worth it, having a slightly slower convergence. Because still, this is still quite fast. And there's an example of this done involving square root of 2. You can see the number of correct decimal places. It doesn't double each iteration, but it comes pretty close. So it's really secant method that's the most popular, easiest to use. In fact, that's in my own research, that's the one I have used for this reason. That's easiest to apply and still converges pretty rapidly. Okay, so that's the end of chapter 10. So I'll keep going on Thursday.